Hi, this is Nasnyanevsky. So we're doing monoidal category theory. We're up to section 6.3. Last section we went through a lot of different coherence theorems, which shows the relationship between monoidal categories and strict monoidal categories. Very nice. What we're going to do now is like a little musical interlude, okay? And ask the following question: what happens when coherence fails? So that's what we're doing here. I just have to say, personally, this is my favorite section of the entire book, and for a very simple reason. It's about work that I did in my thesis, so it's my own personal favorite. Anyways, and it shows the importance of coherence theory. It shows what coherence theory is all about. It's not just a few conditions, and if these conditions work, then the theorems work. No, there's a whole structure here. Coherence theory is the beginning of a whole, coherence theory for monoidal categories is the beginning of a whole field, a whole interesting branch of mathematics, computer science, physics, whatever. Okay, so I took the liberty of drawing this thing. So let's work in a nice, simple category that everyone feels comfortable with. So let's work in vector spaces, okay? And so you have vector spaces, and let's say you have three different vectors spaces, w, x, and y, okay? And you can associate them this way, or you can associate them this way. Okay, and there's a nice reassociator here. Okay, so there's a nice reassociator that goes like this. Now, the usual way of thinking about this is as follows. You take little w and the pair little x comma little y, okay? And if you want, you don't have to think about this. Well, okay, fine. So you can think about this in terms of sets, okay? So here's a typical element here, if you'd like, okay? And here's a typical element here, okay, comma x, okay, comma y. Okay, here's a typical element of this, take a typical element of this, and the alpha, if you're intelligent, would be this guy goes to this guy. Very nice. Okay, and it's not hard to see that if you follow around the McLean-Stasheff coherence pentagon, 1, 2, 3, 1, 2, 3, and you move the arrows following this alpha, and you move the parentheses around following this alpha, that this will commute. Okay, and that's the beginning of coherence theory, that it commutes, and hence, let's go further, the tensor product in vector spaces is not strictly, but there's another category in which it is strict. Okay, and so we might as well think of it as strict. That's coherence theory. Okay, but now let's ask another question. What happens if instead of doing this, I do an alpha prime, okay, or an alpha prime, okay, which instead of going like this, which is the same thing to do this, minus 1 times that. Okay, all right, so that's a very interesting thing. It's still an isomorphism, okay, so all these maps are still isomorphic. These are all isomorphisms. Very nice, we have 5 isomorphisms. Okay, there's still isomorphism, but lo and behold, this doesn't commute. And it's very easy to see that this doesn't commute because, you ready? If you go here, you can have wxyz. That's going to go to wxyz, which is minus 1. Okay, this is going to go to plus 1. This is going to go to minus 1. Okay, so this is going to go to, if you have a little w, little x, w, y, wz, it's going to go following this along. It's going to go to minus 1 times little w, little x, little y, little z. However, if you go here, it's going to go little w, little x, little y, little z is going to go to little w, x, y, and z, minus 1, and here it's going to go to plus 1. So it's not going to commute because this is going to get you to minus 1, and this is going to get you to plus 1. Okay? Simply because there are 3 maps here, and there are 2 maps here. So that's very cool. Cute. Okay? So little arithmetic shows you it doesn't work. Now, just want to show you, it's a very interesting thing, but this doesn't commute with this alpha prime. However, watch this. Go around this whole thing, and these are isomorphisms. So go back like this, and come around like that. Okay, so go around it once. Okay, clockwise, or if you want to go counterclockwise. So let's see what happens here. You're going to have w, x, y, z, go to minus, go to plus, go to minus, go to plus, go to minus. So if you go around, you're not going to come back to the identity. However, if you go around twice, you will. Let's go through it. 1, minus plus, minus plus, minus plus, minus plus, minus plus. You come back to the identity. So this doesn't commute, but if you go around twice, it'll commute. Okay, and that's for a very simple reason, namely minus 1 to the 10th power, because that's how many maps you had to do, is equal to plus 1. As opposed to that, minus 1 to the 5th power is equal to minus 1. Okay, 3rd grade arithmetic. That's the consequence of 3rd grade arithmetic. So this is something I studied in my thesis, okay? And the idea is as follows. I'm going to say this a few times. Coherence is not a toggle switch. It's not it happens or it doesn't happen. Many things can happen, okay? And so I can come up with other examples where this doesn't commute if you go around twice, but it'll commute if you go around 7 times or 19 times or anything like that. For any n, you can do that, okay? So we talk about this, a failure of coherence. So if coherence fails, what do you still have? And the answer is you can have a lot, okay? But forget about the category of vector spaces now. In general, whenever you have such a pentagon, you can expect that it will commute. It will not commute, but it commutes around twice. It commutes around n times for any n, or you can say it never commutes. Okay, these objects could be infinite. It can never commute, and those are all legitimate types of things. In my thesis, I called these obstructions to coherence. Okay, I think that's the title of my thesis. You ready? Namely, to what extent does something not cohere? Okay, so we're always talking about things cohering, getting along with each other. Okay, the natural transformations get along with each other, but what does it mean when they don't get along with each other? So that's what this is all about. Okay. Now, I just want to show you another way of looking at it. Let's say you have the pentagon, okay, and it commutes. The way to think of that as commuting is that it's not a pentagon around, but it's a filled-in pentagon, okay? And there's exactly one path from here to here, okay? As opposed to that, if it never commutes, that means going this way and going this way are 2 different paths. So this is coherent, this is not coherent, or totally not coherent. Of course, there's other types of geometries that you can think of where you can go around this twice and it'll commute. But let's not talk about that. Great. What does that say about the higher associahedra? Okay, so let's just remember, that's that shape, that's that shape. For 3, it's one straight thing. For 4, it's like that. And for 5, it's this sphere that's made out of pentagons and squares, several pentagons and several squares. Now, if you assume that it commutes, then the sphere is kind of filled in. I mentioned this before, but if you assume it doesn't commute, or if you don't assume it commutes, then the way to think of it is that there's different ways, there are different paths to go through. Okay, so let's look at the A5 for a second and think about it. I'm not going to draw the whole thing, it's drawn in the book, okay? But it's going to be a sphere that doesn't necessarily commute, so it's not filled in, and it's made out of pentagons and squares. Okay, several pentagons and squares. Now, let's assume for a second that the alpha here's your alpha is natural. Okay, the alpha is natural, which means that, okay, this commutes, okay, which would mean that the squares commute out of naturality. But if you don't assume that this commutes, then it's not a full sphere, because you're going to have a lot of empty pentagons there. Okay, so the shape you get is a sphere with squares on it. The squares commute, or the squares are filled in. Okay, so if we want, you could think of squares as filled in, if naturality is assumed, and then you have pentagons where the pentagons are not filled in. Okay, so that's what you get. Okay, great. That what I did in my thesis was I actually calculated what these shapes look like. These shapes of these unfilled, what these shapes of these unfilled associahedra look like. Okay, and again, the shapes of the filled-in associahedra are very simple. They're all spheres, n-degree spheres, 3-dimensional spheres, 4-dimensional spheres, 5-dimensional spheres. Okay, just want to tell you, so they're all spheres, which means they're in some sense trivial. Okay, what I did in my thesis was I calculated the shapes of all of them where the squares, where the pentagons are not filled in. Okay, and something that we'll see later on in chapter 9, we'll talk about homotopy theory, and what I did was, there we'll see something called the fundamental group, which is a way of describing certain shapes. And so I calculated the fundamental groups. For all these different associahedras. So these partially filled in associahedras. Okay, and that was very, very interesting. Okay, but I want to tell you what I found. Okay, and it's quite interesting. Okay, we looked at A7. Okay, so this was my thesis advisor was a man named Alex Heller, who I've mentioned before, and he was the one who suggested the problem, and he helped me along the way. Okay, so we had A7. So A7 is about 70 different things, A, B, C, D, E, F, G, okay? And so there's lots of different ways of parenthesizing A, B, C, D, E, F, G, but let me just show you one of them. Okay, now I use square brackets in some of them and round brackets in another. It doesn't make a difference, okay? We're talking about parenthesizations. It doesn't make a difference whether I use square brackets or round brackets. But, okay, what I'm going to do is I'm going to have two reassociations coming out of here. Okay, the alphas, which deal with the round brackets, and the betas, which deal with the square brackets. okay? And I'm gonna move these around. Now, I'm not gonna do it here because you don't need to see me do it here. It's done in the book and it's overly technical. The point is, you're gonna get a reassociation here where the square brackets are moved, and you're gonna get a reassociation here where the round brackets are moved. Great, but you can also go here and move the round brackets here, the square brackets here, and you can also go here, and you're gonna get another reassociation. But you keep on going. Okay. Now, each one of these squares commute because alpha is assumed to be natural and beta is assumed to be natural, so they all commute. So the squares commute, but you get something like this. Again, alpha, 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 beta, 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 beta. Okay. Now, we can continue this. Let's say these two betas are the two bottom parts of the pentagon. Well, then we can go on and talk about the three maps going up. Okay. And so this whole thing will be a pentagon. Well, I'm sorry, this whole thing will be the pentagon. The beta pentagon will be here. Okay? Similarly, here you have an alpha, here you have an alpha. You can keep on going, that way and have three alphas this way. Okay, so it doesn't pay to draw the whole thing, but let me show you what you get. You get 1, 2, 3, 4. Whoops. Yeah, I don't have to show you because it's in the book. Okay. It's on page 312. You have, I work out very clearly what 4 boxes are, showing you with the subscripts how the little parentheses move around. Okay? And if you do it 5 this way and 5 this way, you get what's shown on page 311. And so I show the whole thing on page 311. Okay. Main point is, let's say you go positive, positive, so these two, and then negative, 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 3. So going around, this way, and then do the other side of the pentagon. The other side of the pentagon is here, here, and here. Okay, so here you're going to do beta, 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 and then you're going to do beta, 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 inverse. Beta, 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 inverse. Well, you're going to get back to the same place. So what happens is this top guy is going to be the same thing as the bottom guy. Now, the same thing you could do with the alphas also. Alpha, 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 and then alpha inverse, alpha inverse, alpha inverse, alpha inverse, alpha inverse, alpha inverse. That goes like this. And so you're going to get 5 maps this way, 5 maps this way, and you're going to fill in all the 5, the whole grid. Okay, great. What the hell does that mean? What the hell is this all about? Well, notice this guy is the same as this guy. So we're going to take this whole piece of paper, okay? We're going to take this whole piece of paper, and this guy is the same as this guy. The second guy is also the same as the second guy over here. So this parenthesization is the same as the parenthesization here. And the third parenthesization is the third, et cetera, et cetera. All 5 of these parenthesizations are the same. So rather than, so again, because if you do doom, boom, and go around, you're going to have the same parenthesization. So take this and fold it, make it into a tube. Okay, make it into a tube. Not going to be good with this. Like that. Okay? This is the same as this. So take the piece of paper and fold it into a tube. Very nice. But we have something else going on here too. Namely, this guy is the same as this guy here, past all 5 of them. In other words, this is the same as this, and this is the same as this. Okay, and the 5 parentizations over here will be the same as the 5 parentizations over there. And so you can take this tube and identify this guy with this guy. In other words, take the tube and bring it around like that. Okay, and you get a torus. A torus, or what we New Yorkers call a donut. Okay, key point is every one of these squares are filled in, but the torus is not filled in. Okay, the torus is not filled in, so it's like a blue. What is it called? It's like a tube in the swimming pool. The outside is all filled in, but the inside is empty, okay, like a tire. Okay, it's empty because we don't assume that the pentagons commute. Okay, if the pentagons commuted, then all these things would all commute inside. Okay, and you'd be so again, we're not assuming that this whole thing commutes. We're just assuming this is connected to, this is the same as this, the top is the same as the bottom, so you can identify them, but we're not assuming they commute. We're not assuming the pentagon commutes. Okay, so this is a shape that's in A7. It's not in A6, okay? In terms of fundamental groups, A6, the fundamental group is still free. A7 is the first time where you can do this maneuvering. You can do this maneuvering of the parentheses such that you can do them 2 different ways without intersecting each other, without bothering each other. So basically, you're moving this way and doing a pentagon, you're moving this way and doing a pentagon, you bring them together and you get a torus built into your system. I remember when I came up with this was absolutely shocking. And again, so this is a shape within A7. It's within every time you do, whenever you're dealing with parentheses, associativity is something you learn in 3rd grade, but I thought this was absolutely fascinating. Great. And of course, in the higher, you have even more strange shapes. And so the fundamental groups are not free. So this associativity is quite an interesting phenomenon. Extremely interesting. Okay, good. What else can we talk about? Well, okay. Again, there are many other topics in this section, and I'll talk about them. I just want to go through a main point. The main point is as follows. You can assume that alpha is the identity. Okay? In that case, what you're dealing with is a strict monoidal category. Okay? You can assume that alpha is an isomorphism. In that case, you're dealing with a monoidal category, what we've been dealing with all along. But you can weaken that notion also. Okay, so, and one of the things is we assume it's iso, and we say, and the pentagon commutes. I didn't even bring up the notions of the unit and whether or not those commute, but it's discussed in the thesis. But here's another thing. Just think that alpha is a morphism. What happens if you weaken the notion of a monoidal category such that alpha is not necessarily an isomorphism, it's just a morphism? Okay, so that shows up in the literature. It's called a pre-monoidal category. Okay, sometimes it's also called a skew monoidal category. A skew monoidal category. Okay, it's like a little bit off. Okay, and there are theorems about this and lots of stuff that show up, and there's applications for this. Believe it or not, it shows up in something called quark confinement in physics, and I have a reference to it in the book. The main point is as follows. Coherence is not a toggle switch that's go on or off. There's many different levels of coherence, and that's what's dealt with here. Okay. Let me just tell you about the rest of my thesis. Again, I mentioned it in the book, but it's the rest of my thesis. What about these? These mapping funnels. Well, it turns out, in my thesis, I did the same thing for monoidal categories I did for mapping funnels. Namely, let's assume the mapping funnels are an isomorphism. However, the hexagon does not necessarily commute. Okay, and you get big ugly shapes with this. And again, some of them commute because of the boxes, because of naturality. Some of them commute if you assume that the categories they're coming from or going to are monoidal. So you're going to have the pentagons commute, but the hexagons won't commute. And so I go on and I develop the whole thing here, and I get the shapes for these higher dimensional hexagons and what they look like. This was the second half of my thesis. It was never published anywhere for reasons that I don't know, but it was a very nice calculation. My goal in life was to do the following. The idea is as follows. Let's say you have a category A, okay, and it's monoidal. Then there's another category called A strict that's, and we saw this in last section, that's monoidally equivalent to this. Okay, so you have a monoidal category that's monoidally equivalent to this. Okay, well, let's say you have a category that's not monoidal. So this is monoidal, this is strict. Okay, and this is monoidal equivalence. Well, let's say the category is not monoidal. Okay. Okay. And you have another category where A strict. Okay, so this is strict. So let's say it's weaker than monoidal. Can I say that there's an equivalence, but it's not made out of nice monoidal functors where the hexagon commutes? Maybe you need weaker things to bring this into this. So make this from a not monoidal category. So right here, it works out very nice. Monoidal category, monoidal functor, strict monoidal category, very nice. And so we say every monoidal category is monoidally equivalent to a strict monoidal category. What about a monoidal category? What about a category where it doesn't necessarily have that the pentagon commute? Well, maybe there's another type of weak monoidal functor which makes this an equivalence of categories. Anyways, I never was able to do that. But I thought it was an interesting project at the time. Okay, great. So this is all about monoidal categories. What about other things? Well, we're going to see in chapter 7, we're going to... Okay, we talked about symmetry here. Okay, and this is a reassociation. Okay, in chapter 7, we're going to talk about weakening this symmetry. Okay, and basically, one of the requirements, the coherence requirements, we had this requirement that gamma is its own inverse. Well, let's say we weaken that. So then we're going to get a whole new thing called braided monoidal categories. And we're going to spend a lot of time in chapter 7 talking about this. And it's applied all over. Okay, braided monoidal categories is something very, very much applied, very much in physics, in computers, etc., etc. They show up all over. So again, we're weakening this notion of coherence for a symmetric monoidal category. We get braided monoidal categories, and they're important. Okay, and just again, I've mentioned this word a few times. So coherence theory is sometimes called higher dimensional algebra. The idea is as follows. Algebra tells you about operations. These are about transformations between operations, okay, and how they cohere with each other. And what I'm trying to say in this section is there's a lot of variability there, and because that, it's a very powerful tool. Just like algebra shows up everywhere in science and math, so too higher dimensional algebra does and will show up everywhere in science and math. Okay, but you have to see it. Again, coherence is not a toggle switch. You have to see it when it fails. It's more like it's a whole dial. There's a whole hierarchy of different types of conditions that one can put on it. And it's a whole new world. Anyways, ladies and gentlemen, it's a pleasure talking to you. Thank you.